Good morning friends. I hope you are following the thermodynamic video lectures. So today we are going to learn about the one of the important topic. It is specific heat capacity at constant volume. So to define this one, let me start with the explanation manner. So at constant volume, the gas is at constant volume. We are defining the specific heat at constant volume. So to maintain the substance is at constant volume, we are assuming that one cylinder is there like this. In the cylinder, one ideal gas is there or any working substance is there, that is the gas. So the movable system can be moved on the frictionless surface of the walls of the cylinder. To maintain the constant volume of the cylinder is confined with the stoppers. Here is the stoppers are there. The two stoppers can hold the cylinder, the piston at a constant volume. They cannot have the provision to expand, or they cannot have the provision to expand the gases inside the cylinder. Now the bottom of cylinder is a conducting material. So it is a diathermic walls. The surface of the cylinder is bottom of the surface of the cylinder is a conducting material. So the cylinder bottom surface is contacting with the high temperature of the substance. This is the temperature is very high. So then the lot of heat can be flow from the high temperature area to low temperature of the gas inside the system. When the temperature the heat energy is flowing into the system, then the temperature of the system must be rises. How much amount of temperature is rises in the cylinder? We are assuming that dt. What we assumed here means we are supplying the dq amount of heat energy in the system, then the temperature of the cylinder is increased by a dt. Then the number of moles inside the system, inside the cylinder is having the number of moles is the inside the cylinder is n is the number of moles of the cylinder. So we already known about that one. So for this, if we are supplying the dq is the nothing but it is a small amount of heat energy to the supplying the system. It is a small amount of heat increasing in the system is equal to dt. So now what I am assuming that if the specific quantity of heat energy is supplied into the system, so then we are supplying the specific amount of heat energy into the system. That amount of heat energy is equal to, let's assume, q. You can take dq or q, there is no issue about that one. Now the amount of heat energy dq, or we are taking the amount of heat energy q is the supply to the system. The absorption of heat energy by the system is directly proportional to the number of moles present in the container. Here is the number of moles are present in the container. So if more amount of moles are present in the container, then more amount of heat energy can be absorbed from the hot substance of the surrounding, from the bottom surface of the cylinder. Once again I am repeating, the amount of heat energy absorbed by the system or by the gas is directly proportional to the number of moles inside the cylinder. That means more number of moles are available in the cylinder, then more amount of heat can be absorbed by the system. This already well familiar for in the practical. The amount of heat energy is directly proportional to change in temperature of the system. That means if the more heat energy is increased by the system, then we feel that then it is the indication that the more amount of heat energy is absorbed by the system, that is equal to dq or is directly proportional to dt. This is the equation number 2. Then we are combining these two equation. Q is directly proportional to n into dt. So n into dt. Now I am removing this proportionality constant, that is equal to the, as we are performing this total experiment at a constant volume, so there is no any provision to expand this gas. Then one constant parameter is there. That constant parameter we are introducing is Cv. Cv is the constant. It is the specific heat of gas at constant volume. Then n into dt. Then our goal is to define this CV value. So to define the CV value, what we do means keep the CV value on the left side and send this all on right side. Then CV is equal to, just I hold this CV this side, I am sending this N and dt to other side, but I am writing CV in the left side and remaining terms on the other side. Then Q by N into dt. Then CV can be equal to Q when N is equal to 1 and dt is equal to 1. Then CV is equal to Q, that means amount of heat energy supplied to the system is equal to the specific heat of capacity at constant volume. If N is equal to 1 mole of the gas we are taking, then dt is equal to change in temperature of the gas is equal to 1 degree change in temperature. Now, if we come to the definition manner, what we get the definition manner means what I written here, CV is equal to Q divided by dq or Q divided by N into dt. Then CV is equal to Q or dq when if N is equal to 1 mole or dt is equal to 1. So N is equal to 1 means 1 mole of the gas is there, 1 means the rise in temperature is equal to 1 degree. In a definition manner, the amount of heat required to rise the temperature of unit mole of gas by unit degree at constant volume is called the specific heat of gas at constant volume, is called specific heat of gas at constant volume. This is the definition for this specific heat of gas at constant volume. Now come to the what are the importance of the important points to remember in specific heat of gas means at constant volume means now we will use the first law of thermodynamics. What is the first law of thermodynamics is saying the amount of heat supplied to the system is equal to, it is a sum of change in internal energy and external work done dW. Now you already well familiar, dW is equal to, it is the P dV, but in our present case in CV case what we are doing, the volume of the gas is maintained at constant volume, maintain is the constant, then the dV change in volume must be constant, then P into dV is equal to final volume minus initial volume is equal to P into V minus V, that is equal to 0 because of we are maintained at constant volume as constant volume we are performing. Then the first law of thermodynamics dW is equal to, then first law of thermodynamics dW is going to be 0, then dQ is equal to du plus 0 will come, then dQ is equal to du. What is the conclusion we observed in this situation means at constant volume the amount of heat supplied to the system is utilized only for the rise in temperature of the change in internal energy of the system. That is the conclusion is the amount of heat at constant volume the amount of heat supplied to the system is used to change in internal energy of the system, This is the one conclusion we will get. So then we already known that one, what is the internal energy of the formula means so then the amount of heat we already known that one dq at CV is equal to dq at constant V is equal to constant formula is equal to, so the dq is equal to just we recall that formula. What is the formula we are having? That is equal to dq is equal to n into CV into delta T is there. Then in the previous case, let we go to the back one. So what is the formula here? Having dq or du is equal to NCV delta T is there, that formula I am using here. So then dq is equal to NCV delta T is there, but as per the first law of thermodynamic we already known that one, at constant volume dq is equal to du, then NCV delta T is equal to du. This is also very important formula. The change in internal energy of the system at constant volume is equal to number of moles of the system and constant specific heat of gas at constant volume and change in temperature of the system. This formula we need to use this one. So we have the one more formula, the CV in the degree of freedom also formula is there. So we have the one more formula is there. So we know the change in internal energy of the system is equal to du, or du is equal to Nf by 2 into R into delta T. This formula also is there. So let me take, this is the equation number 4, the equation number 5 we are taking. By comparing these two equations, then CV is equal to CV is equal to R F R divided by 2. This is the formula for the CV. The specific heat of gas at a constant volume, the CV value is equal to the Fr divided by 2, where F is equal to degree of freedom of the gas, degree of freedom of the gas, degree of freedom of the system or degree of freedom of the gas, where R is equal to ideal gas constant, constant. Then come to the, we already well familiar with this one. So the degree of freedom for the monoatomic gas, what is the value? So F value, so CV value, du value for different cases we are taking. So the specific CV value for different type of system, different type of systems. Now let me start with the first system. It is a monoatomic gas I am taking. Let me take monoatomic gas we are taking. What is the degree of freedom for monoatomic gas? So the degree of freedom for monoatomic gas, F is equal to, we will get the 3 value. That implies then CV is equal to question mark. CV basic formula we are having, CV is equal to Fr divided by 2 is there. As F is equal to 3, then 3R by 2. This is the formula for the CV value for the monoatomic gas. Now let me go to the diatomic system. Diatomic gas, when the system is a diatomic system. So we already known for diatomic system, degree of freedom value, F is equal to, what is the value? So we are having F is equal to 5, then CV is equal to, what is the formula? Fr divided by 2 is there. For diatomic system, CV is equal to 5R by 2. This is the formula we are having. So if we take the triatomic system or polyatomic system, so polyatomic system, or we can call it as the triatomic system. So the triatomic system, it will having the two methods. One is the linear and non-linear we are taking. I am taking the non-linear, I am taking linear structure is there. Triatomic system linear structure is there. So triatomic system, linear case, what is the F value, degree of freedom is equal to 5 we are getting. So triatomic system degree of freedom 5 we are getting. Then CV is equal to Fr by 2. Substitute the F value in this one, 5R by 2. So now if we go to the triatomic system for non-linear case, triatomic system or polyatomic system, non-linear case I am taking. So triatomic system or non-linear case system, triatomic non-linear case, what is the F value? F value we are having the f value we are having the 6 value, so the degree of freedoms are 6 value. Then what is the CV value? CV is equal to fr by 2 we are substitute, then so that is equal to 6r divided by 2, that is equal to, simply we will cut that 3r. CV is equal to 3r. These are the values. Let's assume we need to recall this everything one simple table. So what is the value? CV value is equal to, first what we will get, so let me go to the back. So what is the monoatomic system? 3r by 2, diatomic system 5r by 2, polyatomic system 5r by 2, and polyatomic system linear is equal, non-linear case is equal to 3r. So CV values is equal to 3r by 2 for diatomic system, 5r by 2 for diatomic system, sorry, monoatomic system, diatomic system. So 5r by 2 polyatomic system, non-linear linear case. So 3r is equal to linear non-linear case. That is the mono. This is the monoatomic system. This is the diatomic system. It is the polyatomic system. Polyatomic system linear case. Linear case. So polyatomic system non-linear case. Non-linear case. These are the values for the CV values. So they will give them, they may ask the question, they will have what is the CV value of the different gas or different system in terms of R, they may ask the question. So we need to remember these values. So accordingly we need to approach the problem. So thank you. I hope if you are is the first time of the visiting of these lecturers, so I am requesting you, if you feel that these lectures are comfortable for your preparation, then I am requesting you, please share these videos to your friends, and I am requesting you subscribe. Thank you.